Swayam Prabha. Digital India. Educated India.
Hello, I am Ajit, and once again I'm here to assist you in this course of Introduction to Experiments in Flights. Okay, so in this tutorial we will be learning about the parameter estimation using aircraft data. So the experiment which we will be learning today is this: aerodynamic parameter estimation using least square methods. Here you see these two terms got introduced first time, maybe parameter estimation and least square methods. So I'll be talking about what is parameter estimation, why it is required, and how to do the parameter estimation, and some of the techniques we will discuss. So here I'll discuss about least square method. So we will learn what is least square methods and how it is applied for parameter estimation. With some examples, so I'll show you some examples. So let us start with parameter estimation. Parameter estimation. Okay. So what is parameter estimation? How can we understand it, or how can we define it? So parameter estimation is nothing but a subset of system identification. So you can write it is a subset of system identification. Right? So here you saw this term system identification. So what is system identification? So system identification is about the identifying the model with the help of input and output data, right? So let us understand this. So suppose here you have set of input data. So I'll write input and output data sets, and this is the model, right? So once you have sets of inputs and output and you are trying to identify the model, so this is basically a problem of system identification. Now, so once you got this model, and if model is structured in terms of unknown parameters, then identifying parameters can be a problem of your parameter estimation. So how will you define the parameter estimation? It is like this: if model is structured, with unknown parameters, then identify parameters is parameter estimation. Okay, so this is how you can define the parameter estimation. Now you can take some simple example also, like a very basic model. I'll just show you, which is called the spring mass damper system. Damper system. Yeah. So all of you know it is expressed like this. So mx double dot plus bx dot plus kx equals to some force, right, here. So each notation will have the standard representation. This is mass. This derivative is called damping coefficient, right, and this is spring constant. Here your x is, let's write in terms of t, is displacement, and ft force. Okay, so what we observe in this kind of structure, this is, you see, like this model is structured with the in the form of parameters. So here m, b and k can be the parameter for this model. So how will you augment this problem in the parameter estimation? Here you can say, suppose now ft is the input and the displacement is observed output. So with the help of input and output, means for data for the force, applied force, and displacement, if you can identify mass b and k, then it can be a problem of parameter identification or parameter estimation. So this was a simple example. And now next thing come, why do you need parameter estimation? So this was about what is parameter estimation. So next thing comes why parameter estimation. Let's write PE is required. Okay. What is the motivation behind parameter estimation? So as we know, most of the design algorithm, and if you talk about control design, guidance design for the aerospace application, and design of aerodynamic database, if you want to detect the fault in the system or you want to identify the faults, then you need an accurate model, and accuracy of the model depends on the parameters. Like if model is parameterized, then accurate estimation of parameter is equally important. In that way, we should know what are the accurate parameters, and then with that we can have the accurate model. So next thing now will come, how to do the parameter estimation. How to do parameter estimation. So we talked about what is parameter estimation and why it is required. Now next thing comes, how can we do this parameter estimation, right? How to do the parameter estimation. So various models are available. If you see the literature, then model can be classified in two categories. We talked about the system identification. Then observed model can be of two types. So first type is called phenomenological model, which can also be called like physics-based model, physics-based model. Right? And then next is your black box model. So I'll tell you the difference. What is the difference between these two methods, these two class of model. Black box model. Right? So under physics-based model, there are several model methods available for parameter estimation actually. So let us try to understand what is physics-based model and what is black box model. So in the class of physics-based model, where we have the basic understanding of the physics, we can derive the system with the physical understanding of system. So this will fall in the category of physics-based model. Next class of model, black box of model, where we don't know anything about the system. Like we have no knowledge about the system. We just have inputs and then observed outputs. But system is like a black box, so that's why it is called the black box model. Now if you want to do the parameter estimation of these two categories, so several methods are available. So I'll list few of the methods here. So under this category there are methods which is called equation error method, equation error method, Next is output error method. Okay, and other method can be your filter error method. Okay, so in this category these are the methods. It depends like what kind of system you are dealing with. So application of this method depends on the system, also complexity of the problem. Suppose the data which you acquired, input sets of input data and output data, they are kind of very accurate. In most of the aerospace application we see instruments are of very high quality, so you don't see much noises in the data. So there you can apply this equation error method, assuming there is no noise in the instruments and in the process. So when there is no measurement noise and process noise, so this method is preferred. Suppose there is some error in the instrument, like your instruments are not functioning well, it means you have measurement noise available, then output error method is preferred. Their output error method can be a best option. This next class of error, filter error method, where you have noise in both the thing, like process, you have process noise as well as the measurement noise, then you can go for filter error method, right? And next class of model is the black box model, where as I discussed, as I said, like we don't have the physics understanding for this model. So under that, several methods can also be listed. So I'll just write few of the methods. So first method can be of your artificial neural network based, artificial neural network. Second can be a fuzzy logic based. Okay, and third can be combination of these two methods. So it is said neurofuzzy and other methods can be your support vector machine, SVM, and many more methods are there. So you can also write about machine learning based method. Machine based methods, right? So these all are your black box models. So I'll not discuss everything in the detail. So what I will do, like I'll take one method from this class, which I'll say least square. It is also called regression analysis. So least square method will fall in this category, equation error method. So least squares. Method. And from this I'll take a very popular method which is proposed by Professor Ghosh, and it is called delta method. So we'll learn what is delta method and how it is used to estimate parameters, right? Delta method. So I'll start with this least square method. So let's see what is least square. So this is a least square based method. So I'll write least square estimation. The idea of least square estimation has been proposed way back by a very renowned scientist, Carl Gauss, in 1809. Okay. So what is the basic principle of least square estimation? Basic principle. What actually do we mean by least squares? It has been a very popular method, and It is not limited to the application of parameter estimation or system identification. It has been widely used for various kind of problems, right? So least square estimation says it minimizes the sum of squares of the error between measured output and model response. Yeah. See, it's a very catchy term. It is about minimizing the sum of squares of the error. You see. Now, what is the understanding behind it? Like, what is the inference of this statement? It minimizes the sum of squares of the error. And why sum of square of the error? Why not absolute error? So let us try to understand that. So if you have some data, I'll start with a very basic example. This one, here, here, and here. Okay. Like this. You can give the name like Y or X. Okay. So here what we are trying to do, like we have some amount of some data like this. We are trying to fit a curve, a best fit, which minimizes the error actually. So for these values, what could be the best fit? We are trying to understand that with the concept of least square. So can least square estimation help us to find a best fit for this kind of problem? If you see, let us try to make the inference of this statement with this example. So here is the error. Yeah, these are the error. Okay. Error with respect to each data sample, so data point. So once I say squares of the error, then it is something like this. So you make a square here, hope it is clear here, and this. So now you see that how many squares? 1, 2, 3, 4, and 5. You have 5 different squares now. 1, 2, 3, 4, 5. Okay. So summation of squares means like you are adding all the squares. Square 1 plus square 2, third square, 4 square, and 5 square. Sum of all the squares. Okay. It is sum of all the squares. Yeah. Now you want a line, a best linear fit for which summation of squares will be minimum. So that is the philosophy of this least square estimation. So least square works like that. It gives you the line, corresponding line, a best fit line for which summation of all the squares will be minimum. Minimum, right? Now what I was talking about, like why it works on summation of squares of the error, not absolute errors. And before that, if you see the error here, so once you do the square, what it does, like it gives you always the positive value. If we don't do if we don't do the square, what happens, like it can give you some of the negative error, some of the positive error. So once you accumulate all those errors, then what happens, like it will cancel each other. Some big error in positive side can cancel the big error in negative side. So it is very much important to have the positive error. Now next thing comes, why square is needed. If you take the absolute value of the error, that also can give you the positive value, right? It is not necessary that we have to do the square. So what is the theory behind it? Like if you ask any calculus, maybe professor or the students who has taken the course, if you want to minimize something, how will you minimize it? Like, so they will say like what you do, you just take the first derivative, equate to the 0, and you get the solution. You get the minimum value corresponding to that. So it becomes very much easy for us or to deal with the calculus once something is in a square. If you don't make it square, if it is absolute value, then it may be a discontinuous derivative. So it will be very difficult to do the analysis on this discrete derivative. So for that, it is very much useful and easy to work with square term. So the objective function will be in terms of square, which I will be talking now. So next we will see the mathematical formulation. So now I think this should be enough for us to understand about this principle. Yeah. So for least square estimation, we'll talk about the mathematical formulation. So now how will you understand it mathematically or how it works, right? So we'll see the derivation of this least square estimation. So now we'll be learning this mathematical formulation. Okay. So suppose you have n samples of data for the output. So I'll write yi1, yi2. Like this you have n samples. So these are basically your output or dependent variables of n samples. I write here y because I'm assuming this is ith output. Output can be of like multiple output can also be possible. So I'm taking the ith output, so right. Corresponding input variables you can write like x of 1, x of 2, and x of n. So this will be your input variables or independent variables. Okay. So see, now slowly we are progressing through this idea. Like you have input variables or input samples and output samples, and here x is a vector which have x1, which x2, x and q. Okay. So each x has these many inputs. You can write like that. Now we'll make a simplified assumptions here. Assume output are linearly related to input. Okay. Yes. So how will you write? You can write yik equals to, so you have to introduce now the constant term theta 1 x1 k plus theta 2 x2 k, like that theta nq x nq k with some error epsilon k. This is called equation error. Right. Okay. So in the matrix form you can write like this: y k equals to x transpose theta of k, yes, plus epsilon k. Okay. Now if you generalize it, like if you write sample by sample, so y1 corresponding y1 will be your x transpose 1 theta of 1 plus Okay, and the sample will be n x transpose of n in the samples, and then okay. So this is how you will write. Now further in a general form or in a matrix form again, you can write y equals to x theta plus this error. Yes. So this is the matrix form notation, and X matrix will have x1 of k. I'll not use k now. So x1 of first one, x2 first sample, x and q first sample, then x1 second sample like this, this is x and q, and yeah. So now you know y set up all the outputs, x is this, and E corresponds all the associated errors for each samples. So this is the thing. Now we have to estimate this theta, which will be in terms of vector. Theta corresponds all the theta 1, theta 2, theta till nq, right? So how can we estimate this theta with the philosophy of least squares? So what least square estimation says, with minimizing the error, summation of squares of the error, you can find the estimate. So if you write the cost function corresponding to that, so j theta can be written like this: half of k equals to 1 to n E transpose E. So what is E epsilon here? Error. Error is your y minus x theta. So this we know. So now we are trying to minimize the summation of square of these errors, right? So here it is k. Sorry, it should not be like this. First, square of errors, right? So it should be your, this is the one. So square of the errors. Now you can further simplify. You can write epsilon transpose epsilon, right? And once you expand this with this relation, so it will become y minus x theta transpose times y minus x theta, right? So you can also write y transpose minus theta transpose x transpose times y minus x theta. Now if you take the derivative with respect to theta, so dou of j theta by dou theta, right? So yeah, I have missed half. So what happens, like what will happen like once you take the derivative of this? Because we want to minimize, we have to take the first derivative. So it will give you minus of y transpose x plus theta transpose x transpose x. Yeah. And how do you do the minimization? You equate this with 0, right? Equating with 0, what you got? This one. So now if you take the transpose both the side, then it will become your x transpose and theta equals to, here if you take, then it will become your x transpose y. So I'm taking transpose both the sides like this. Yes. So with that you will get theta equals to x transpose x inverse times x transpose y. Okay. So this is the estimated parameters. Okay, so what we got, this parameter vector theta we got x transpose x inverse times x transpose y. So this is your estimated parameter vector or matrix with the philosophy of least square estimation. Okay, so if you want to verify it actually, then as you know this equation, y equals to x theta plus error. If you make this error 0, then it will become your y equals to x theta. Okay, so in this equation what you do, you multiply, pre-multiply with x transpose y, and it will become x transpose times x theta, right? Now your theta will become x transpose x inverse times x transpose y, right? So this is the theta you got with this algebraic manipulation, so which should be like this. Yeah? So you see both are similar. So now you got the expression for theta with the least square. Okay, so let us try to understand the application of this method again, or it can be a exercise problem for you. Suppose the same example I am taking. Let us say y equals to 5x plus 4. Okay, so this is the mathematical equation, linear equation, right? So the structure is what? Y equals to mx plus c, right? This m represents slope and c is intercept. Now to exercise this method, how can you generate, how can you make this as part of your exercise? So what you do, you first generate 1000 samples, maybe, yeah, 1000 samples of data for this, because here we know slope is 5 and intercept is 4. So with y equals to 5x plus 4, you take different value of x, so you will get corresponding y's. So generate 1000 samples of input output data, right? So it means now you have the data, input data and output data, and then your structure is like this. So with that, now you will try to identify those parameters. If I am assuming these are the parameters, m and c are the parameters, can you find m and c correctly? And second, to check the efficiency of this algorithm, you can add the noise in the data. So you will add noise to the data. Right, and then estimate slope m and intercept c, right? So how will you proceed with that? Like now we will try to develop the understanding how this kind of exercise or this kind of problem can be broken into this format, right? So if you see y equals to mx plus c, so you can also write y equals to x1 and m and c. So for this problem, we will have this 1000 samples of the data. So you will definitely be knowing about x, and you have this y data corresponding output data. So now you see this is again becoming the format of y equals to theta x, make it big X, and this is what you want to know, right? So this is the theta. So this is again in the form of y equals to x theta. Same thing. So if you want to estimate theta parameters from this equation or for this data, then use this least square estimate value. You will get slope and your intercept, and you add the noise of different degree, 5%, 10%, 20%, and you see how least square is performing for different sets of data once you raise the level of noise, if you make it higher, so how your estimated values are going to be, is it going to be same or going to be different? So you can do it by yourself. So thank you so much